In this example, we're asked to find a cubic equation with integer coefficients that has no quadratic term and has 2 plus I root 3 as one of its roots. In order to do this, we're going to follow a set of steps. The first step is to find the sum of the roots. So any cubic equation, and this one actually in particular, is written with an x cubed term. We know that there's no quadratic term, so we have 0x squared. We have an x term and then a constant term. And of course the x cubed term and the x term, we don't know their coefficients. And we don't know the constant term yet either. So to find the sum of the roots, we're going to use the sum and product theorem. The sum of the roots is the opposite of the second coefficient over the lead coefficient. So in this case, n, the degree of our polynomial, is 3, which tells us that a sub n minus 1 is a sub 2. That would be the coefficient of x squared. We happen to know that the coefficient of x squared is 0. So it doesn't even matter to us what the lead coefficient is, because 0 divided by anything is 0. Thus, the sum of the roots is 0. In our second step, we find the additional roots. The complex conjugates theorem tells us that 2 minus I root 3 also has to be a root of this equation, because complex numbers come in pairs, or complex roots come in pairs. We know the polynomial has to have 3 roots total because it's cubic, and the fundamental theorem of algebra tells us that. So we're going to let r be the third root. This means that the sum of the roots is 2 plus I root 3 plus 2 minus I root 3 plus our third root r. When I combine my like terms, I get 4 plus r equals 0. And we know that the sum of the roots is 0 because that's what we found it to be when we applied the sum and product theorem. By solving this equation, we can find that r, our third root, is negative 4. Now that we know all of the roots of this polynomial, we need to write the polynomial. In this case, the question asked for a function. We don't have to worry about the a term in front because we could give any function that represents a polynomial with these roots. We're going to write each of the roots as factors and multiply these together. Here you could use the sum and product theorem again to write the quadratic that's obtained when you multiply those last two factors together. I'm going to show you how to do it the long way in hopes that it will inspire you to use the short version in the future. First, we need to expand the second two terms, so I'm going to multiply those together. So I multiply those together using the distributive property. I notice that my last term is 2 plus I root 3 times 2 minus I root 3, which is a difference of 2 squares. So I'm going to use that pattern to multiply those two together. And I'm going through the steps to simplify this down. You'll probably want to write this down on your own so that you can follow along with these steps. You continue to simplify and combine like terms. Make sure that you substitute negative 1 for I squared. Combine any like terms. Now we have a quadratic times a linear factor. Again, you could obtain that quadratic using the sum and product theorem instead of multiplying it all the way out and going through all the steps that I just showed you. As a final part of this step, we need to multiply the two factors together and combine any like terms to obtain our polynomial.